some of the arguments you're going to be evaluating in your thought primer homework are going to look very similar to the arguments we've been evaluating in earlier lectures. They're going to be ordinary language arguments about snow and mail and Cassidy's beer choice and so on and so forth. But some of the arguments you're going to be evaluating are different. They look more like this, where you have a series of already symbolized premise statements stacked on top of a given conclusion. And you're not going to know what statements the letters of these symbolized arguments represent, but you're still going to have to test the arguments for validity using indirect truth tables. Okay. Now you can see if we were going to create an ordinary truth table for this particular argument, we have a lot of lines, right? Because we've got 1, 2, 3, 4, 5. We got 5 unique letters that comprise this argument, and 2 to the 5th is 32. So we'd have a truth table of 32 lines, and that would make it really easy to make mistakes when we're marking in all those T's and F's. We might be able to determine this argument's validity with just a line or 2, though, if we use the indirect truth table method. All right, so we're going to write this entire argument out on a single line, and we're going to assume the conclusion is a false statement and all of the premises are true. And then our job is to look for what would be logically necessary given our beginning assumptions. What would be logically necessary, okay? Now we want to make sure that we have our operator truth tables handy if we haven't memorized our truth functions. So we want to make sure that we have our chapter 4.3, I think, summary handout with us as we do our thought primer homework. And we want to make sure as we're doing this that we keep track of where we are in our work, okay? Now, here's what I mean by that. What I mean is that when we do this indirect truth table method and we're dealing with these really lengthy arguments like this one, it can be really easy to forget what we've done at one end of the truth table. And we might make a mistake like have one single letter represented as both true and false at the same time. So what I've seen folks do that I think is pretty effective is they'll get a number of differently colored pens or pencils, and they'll do their first round of deductions using one color, and then when they can say to themselves, okay, I'm confident I got all that right, then switch to the next color. And that way, if they make a mistake, they can always go back to the point they left off on with the previous color where they were really certain about being right. It's kind of what I do when I teach this class in a classroom. I'll have about 5 or 6 differently colored whiteboard pens, and we'll just kind of use different pens as we work along. All right. So what we're looking for is anything else in this argument that we can know with 100% certainty, a truth value we can know with 100% certainty given our assumptions. And the problem is, or one problem is, these first 2 premises here, they're both horseshoes. And if we look at our conditional statement truth table, we'll see that there's 3 possible combinations of true-false values when a horseshoe is true. So we can't make any deductions about our first 2 premises. But look at this third premise here. Tilde B. Tilde is the main operator here, and we're assuming it's true. Well, if that's the case, then B's got to be false. And if B is false there, it's got to also be false over here. So I know that. So now I'm looking again at the argument. I've got new things in my indirect truth table. Is there anything else that I couldn't know before that I can know now? Can I know, for example, the value of this wedge, knowing that B is false? And we say, well, no, C could be either true or false, A could be true or false, we don't know. But look over here at our conclusion. We're assuming this horseshoe statement is a false statement. And there's only one combination of true-false values that allows a horseshoe statement to be false. And that's right here on line 2. The left side is false and the right side is true. Okay, so that tells me A is true, and it tells me that tilde E is false. Well, if tilde E is false, then E's got to be true. And that means that A and E have to be true anywhere else they appear in this argument. So A's got to be true over here, and E's got to be true over here. And so again, I look at the argument. I'm looking around. Can I deduce anything else now that I have new information in my truth table? I still don't know anything more about this second premise here than I knew before, so I can't make any deductions there. But over here I can. Because we're assuming this horseshoe is true, and we just determined that this A is true. And in order for this horseshoe to be true when the left-hand side is true, the main operator on the right-hand side of the horseshoe has to also be true. That means that wedge has to be true. And if that wedge is true when B is false, that means C is true. And if C is true there, it's true here. And if C is true here, and the main operator horseshoe is considered true, that means that the main operator over here on the right-hand side of the horseshoe has to also be true, which means D would also be true. And look what just happened. We just deduced all of the logically necessary truth values without running into a contradiction, thus proving that it's possible for the conclusion of this argument to be false when all the premises are true and is therefore invalid.